So in this module, phases and phase diagram. So this is the third module of our course of materials engineering. Now in this module, the basic terminologies what we will discuss is the phase. So what is meant by phase? A phase may be defined as a homogeneous portion of a system that has uniform physical and chemical characteristics. So it is a homogeneous portion of system that has uniform physical and chemical characteristics. So we can call in case of equilibrium diagrams. So we will come across different solid solutions and intermediate phases and intermetallic phases. So obviously when we call phase means that particular region or that particular component or the portion has uniform physical and chemical characteristics. Then equilibrium or constitutional diagram. So this diagram, it gives the information about the control of microstructure or phase structure of a particular alloy system is convenient and concisely displayed in what is called phase diagram. And it is also called as equilibrium or constitutional diagram. So means it is a information about the control of microstructure or phase structure of a particular alloy system. So means we will get the information about the different equilibrium structures present in a given alloy system. Try to understand, it is equilibrium structure. So means the phases which are in equilibrium, those phases can be visible or those phases can be seen in case of equilibrium diagram. The phases which are not in equilibrium, you will not see those phases in a constitutional or equilibrium diagram. Then solid solution. We have discussed solid solution in strengthening mechanisms, but just to recall, it is a homogeneous mixture of two or more metals in solid state, and solid solutions has two types: substitutional type solid solution and interstitial type solid solution. We have already discussed solubility limit, but again we will recall here. It is the maximum concentration of solute atoms that may dissolve in the solvent to form a solid solution at some temperature. Then binary system. So here we have two binary systems. So binary isomorphous system and binary eutectic system. Binary isomorphous system. An alloy system that contains two components that attain complete liquid and solid solubility of the components. For example, copper nickel alloy. It is the simplest binary system. Try to understand. An alloy system that contains two components that attain complete liquid and solid solubility. So means all the Hume-Rudry rules are satisfied in case of copper nickel system. We know that all the Hume-Rudry rules are satisfied. So that's why in case of copper nickel system we have complete solid solubility, and obviously it has complete liquid solubility. Liquid solubility means we cannot separate two liquids. If you mix water and kerosene together, it is a liquid solution, but we can see liquid, water different and kerosene different. Similarly, oil and water. If we add oil into the water, you can see oil separately and water separately. So means incomplete liquid solubility. But here in case of binary isomorphous system, we have complete liquid and complete solid solubility. Then binary eutectic system. An alloy system that contains two components that has a special composition with minimum melting temperature. So remember the term minimum melting temperature. For example, lead tin aluminum silicon system. If you look at the melting point of aluminum is around 660 degrees centigrade, and melting point of silicon is above 1000 degrees centigrade. If you add aluminum and silicon, if you add silicon into the aluminum, what will be the melting point? So this melting point, because already the curious question comes into the mind, what will be the melting point of this aluminum silicon alloy? So this melting point can be can be find out by using the phase diagram. And if you see the aluminum silicon phase diagram, you will see that around 11 to 12% silicon, the melting point is lowest melting point observed in aluminum silicon alloy system. That is around 550 degrees centigrade, silicon will melt into the aluminum. That is the lowest melting point observed in aluminum silicon system. So this lowest melting point we call is a eutectic point. It is the eutectic point. So it is a eutectic point means lowest melting point observed in that particular alloy system, above which, so above eutectic point, the alloy is in liquid state, and below eutectic point, alloy is in solid state. There is no liquid plus solid state present for eutectic type alloy. Means there is no viscous region present in case of eutectic type of alloy. Directly solid converts into liquid, and liquid directly transforms into solid. So lot of examples are there for eutectic system. One of the popular exam is lead tin, aluminum, silicon. Okay, various systems are exhibit eutectic systems. Now with these terminologies in mind, what are the issues to address? When we combine two elements, so what equilibrium state would we expect to get? In particular, if we specify a composition, weight percent copper, weight percent nickel, and a temperature, so pressure we will neglify, we will ignore that part. So means in particular, if we specify a composition and temperature, then what equilibrium state would we expect to get? So in order to answer this question, we will also get the information if you know the composition and temperature. So how many phases do we get? What is the composition of each phase and how much of each phase do we get? If you combine, if you see this example, nickel and copper. So this is the nickel atom and this is the copper atom. If we combine nickel and copper atom, obviously it is a complete solid solubility. And we get two phases, phase A and phase B. And if you look at the phase B, it is so phase B is different and phase A is different. So how many phases do we get? So we have got here two phases. What is the composition of each phase is different, and that can be determined by using equilibrium diagram. And what is the percentage of that phase present? What is the percentage of phase A? What is the percentage of phase B? Again, that can be found out by using lever rule. So that we will discuss in coming sessions. So by using this information, easily we can find out if you know the temperature and if you know the composition. So at equilibrium, how many phases are there and what is the state of that phase, that can be easily find out. So in this particular discussion, the Gibbs phase rule plays very important role, because it is a tool to define the number of phases or degrees of phase changes that can be found in systematic equilibrium. So generally, the Gibbs phase rule, it is a F is equals to C minus P plus N, where F is degrees of freedom, C is a component, P is a phases at equilibrium, and N is non-compositional parameter system. So typically, value of N is equals to 1 because we are considering pressure is constant. When pressure is not constant, in that case you can consider N equals to 2. But in our further discussions and upcoming discussions, we have assumed that pressure remains constant. So that's why we will consider N equals to 1. So we'll revise the equation as P plus F equals to C plus 1. If you rearrange the terms, you will get the equation as P plus F equals to C plus 1. And how to use this equation in order to find out degrees of freedom, that we will discuss in the coming sessions. Because this phase rule is very important, because we can use it to predict how many phases can be expected in case of equilibrium states. So this phase rule is very important to predict the number of phases present in a equilibrium state. And using this rule for a given phase field, we can predict how many independent parameters we can specify. So looking at simple phase diagram for sugar water or milk system. If you look at this phase diagram, it is a simple phase diagram. You can see vertical axis in any phase diagram. The terminology is very simple to understand. The vertical axis is always temperature and horizontal axis is the composition. You can see two vertical axes are there where this is 100% water and this end 100% sugar. Okay, and from left to right percentage of sugar continuously increases. So this is the typical template of a phase diagram which is valid for all the system. It doesn't matter sugar water, copper nickel, aluminum zinc, aluminum silicon. For all the phase diagrams which exist in the nature, it shows the same typical template. That is two vertical axis of the temperatures and horizontal axis. Two vertical axis you can see. One is a pure water, another is a pure sugar, and percentage of solute or percentage of sugar continuously increases from 0 to 100, that is left to right. Now, so this is a sugar water system. You can see at around 60% sugar can be dissolved in water at 0 degree temperature. So 60% sugar can be dissolved into the water at around 0 degree centigrade, you can see. So as the continuously temperature increases, the percentage of solubility of sugar into the water, it also goes increasing. So this line we call it the solubility limit line. Why we call solubility limit line? Because left of solubility limit line we have only one phase, that is liquid solution, and right to solubility limit line we have two phases, liquid plus solid. So that's why this line is a limit line between two phases, single phase to two phase. So that's why we call this line as a solubility limit line. And the solubility limit line, you can see the nature of solubility limit line is such that as the temperature increases, the solubility limit also is also increasing. Now we will see the effect of temperature and composition over this solubility limit. So if you change the temperature T, the percentage of phases, the number of phases will also got changed. If you look at this point A, so point A is at 20 degrees centigrade and 70% sugar. So here we have two phases, that is liquid plus solid, because we are in the right side of solubility limit line. So that's why we have here two phases, liquid plus solid. If we increase the temperature, see path A to B, you can see at 100 degrees centigrade, we have only one phase, and that is only liquid. So means, even though we are in the two phase region, but by increasing the temperature, by changing the temperature, you can see the two phase mixture has now converted into single phase. So this is very important. So solubility limit is now increases to single phase region. Now from at this point only, if you change the composition without changing the temperature, if you change the composition 70% sugar, now add 90% sugar into that, again you will get into two phase mixture. So means the conclusion of this slide is that if you change the temperature or if you change the composition, the number of phases can be changed.